Hi, my name is David Tare, and this is my second video on Fibonacci numbers. So in this video, I'm going to provide two more sum formulas for Fibonacci numbers. In my previous video, I provided a sum for the first n Fibonacci numbers. In this one, I'm going to provide formulas for the first n Fibonacci numbers with odd indices and the first n Fibonacci numbers with even indices. So that's where we're skipping Fibonacci numbers. We're skipping every other one. Just to remind you, here's a table of the first 24 Fibonacci numbers. So that's what they look like. So here's the notation I'm going to use. The sum of the first n Fibonacci numbers with odd indices, I call that T2n minus 1, which is just F1 plus F3 plus F5. Notice I'm skipping every one with an even index. And I always go up to F2n minus 1, which is the nth odd Fibonacci number with odd index. And then similarly, we define the sum of the first n Fibonacci numbers with even indices. We call that T2n, and that's just where we have even indices up to 2n, F2 plus F4 plus F6 up to F2n. So I'm going to derive formulas for these sums. And as in my previous video, let's begin by considering some examples to see if we can spot a pattern here. So we start with the first n Fibonacci numbers with odd indices, and when n equals 1, we get T1 equals F1, which is 1, which happens to be F2. For T3, which is F1 plus F3, that's going to be 1 plus 2 or 3. That happens to be F4. Similarly, T5 turns out to be F6. And I think you can see the pattern here. T7 is F8, T9 is F10. You can check these yourself, but I do all the math here. So from the above pattern, it seems reasonable to conclude that for every natural number n, we have this formula down here, formula 3, which says that T2n minus 1 is equal to F2n for all n. So how do we prove that? I mean, I just did it for a finite number of cases, happens to work for these cases, but that doesn't prove this formula. For that, we have to use the method I used in my previous video called mathematical induction. So the way mathematical induction works is we start with a base case, and in this case, the base case is n equals 1. So we already know that this formula works for n equals 1. That's just the first example up here. And we also know that it works at n equals 5, but we only care about n equals 1 here. So we take care of the base case. That's pretty easy. And now we complete our proof by proving the induction hypothesis, namely that if we assume that equation 3 holds for some fixed natural number n, and we already know it works for n equals 1, then it also holds for n plus 1 as well. And the way, just to think about induction to remind you, we know it works for n equals 1, and if the induction hypothesis holds, works for n plus 1, which is 2, and then we keep going, it's going to work for n equals 3, 4, so on, all the way up to infinity. That's how mathematical induction works. So the working with the indices here is a little tricky because we have to substitute n plus 1 for n. So we're substituting 2 times the quantity n plus 1 minus 1, which is 2n plus 1, for what we had before, which was 2n minus 1. That's in formula 3. So the 2n minus 1 becomes 2n plus 1 here. Similarly, 2 times n plus 1 is 2n plus 2. So that becomes the new Fibonacci number index. Notice it was F2n down here. Now it's F2n plus 2. So we have to prove formula 4 holds whenever formula 3 holds. If we can prove this, then we will have completed our proof, because we will prove the induction hypothesis. So anyway, how do we prove equation 4? Well, we just use the definition of T2n plus 1, which is the sum of the first n Fibonacci numbers with odd indices, F1 plus F3 up to F2n plus 1. That equals T2n minus 1. That's the sum of the first n plus F2n plus 1, which is the last one. And using our induction hypothesis, using equation 3, we already know that T2n minus 1 is equal to f2n. That's this formula down here. And so we can substitute that in, f2n for t2n minus 1. And we're still adding f2n plus 1. And now, finally, using the recurrence equation for the Fibonacci numbers, we know that f2n plus f2n plus 1 is equal to f2n plus 2, because every Fibonacci number is equal to the sum of the previous two. That's all this is saying. So that completes our proof. Notice that we have t2n plus 1 equals f2n plus 2, and that's exactly what we were trying to prove, equation 4. So we're done. We've proved equation 3, the formula for the sum of the first n Fibonacci numbers with odd indices, and that's just f2n plus 2. So we did the odd case. Now let's do the even case. So now let's consider the sum of the first n Fibonacci numbers with even indices. So we can look at the first 5 cases. This t2 is f2, which is 1, and that's 2 minus 1, or f3 minus 1. Notice we have minus 1s here. So this formula is a little more complicated than my previous one. It's not just Fibonacci numbers, it's Fibonacci numbers minus 1. But you can check yourself that these other cases also hold. T4, which is f2 plus f4, that's 1 plus 3, which is 4, which is 5 minus 1, or f5 minus 1. In the same way, we see that T6 is f7 minus 1, T8 is f9 minus 1, and T10 is f11 minus 1. So it's pretty easy to spot the pattern here once again. Turns out T2n is just f2n plus 1 minus 1. That's the equation we need to prove now. So we do it the same way. We use mathematical induction again to prove this formula down here, equation 5. And we do the same way. We start with a base case, and we already know the base case n equals 1 works because it's just the first formula here. We actually know it for the first 5 cases, but the first one is enough. So we complete a proof by proving the induction hypothesis, namely that if f formula 5 holds for some n, and we already know it works for n equals 1, then it also works for n plus 1 as well. And once again, we have to manipulate the indices. So 2 times n plus 1 is 2n plus 2. That's going to be this first index, the index on t. And then 2n times n plus 1 is 2n plus 3. That's going to be the index on the Fibonacci number. So if we can prove this formula, equation 6 from equation 5, then we're done. We'll have proved it for all n. So let's do it. All right, so to prove 6, then we do the same thing we did before. We just first start with a definition of Tn plus 2, and that's just all the Fibonacci numbers with even indices up to index 2n plus 2. And notice that the first n of these terms is T2n, so we're really just adding T2n plus f2n plus 2. But now we use formula 5, this formula down here. We substitute that in for T2n. We get f2n plus 1 minus 1. And then we add f2n plus 2 to that. And we just switch around the last 2 terms. On this line, we get f2n plus 1 plus f2n plus 2 minus 1. f2n plus 1 plus f2n plus 2. Once again, using the occurrence equation for the Fibonacci sequence as f2n plus 3 minus 1. And voila, we're done. We proved formula 6. So that completes our proof. And so we draw formulas for the sum in both the even index and odd index case of Fibonacci, every other Fibonacci number. So that's my video. And once again, if you haven't done so, please subscribe to my YouTube channel, which is Dave's Math Channel. And hope to see you again. So thank you for watching.